bears, I've thrown it at kids. The thing is amazing. That last part might not be true. All right. So you got a strong acid. It's one of your 7 strong acids. Don't worry, that won't be on the quiz today. And so your strong acid is going to be aqueous, and it's going to fully dissociate. Sulfur doesn't like to dissolve. Okay, other than a few exceptions. So zinc sulfide is going to be a solid, and then you mix them together. The hydrogen and the zinc are going to switch places. And so I'm going to get 2 hydrogens with sulfur, because hydrogen's a 1 plus and zinc's a 2 minus. And then I'm going to get my zinc with 2 nitrates, because zinc is a 2 plus and nitrate's a 1 minus. All nitrates are soluble. And then yesterday, at the end of the hour, we talked about how sulfur, sulfite, and carbonate, when they're hydrogen, when they're added to acid, become gases. And so this is that stinky, stinky gas that comes out of stink bombs. Okay? And so that's the molecular formula. To make it a net, these guys fully dissociate, so there's 2 of these and 2 of these. This guy does not dissociate because it's a solid. That's what a solid does, it doesn't dissociate. This guy is a gas, so it's going to bubble out of solution. And then this is going to dissociate as well because all nitrates are soluble. So what things are common on both sides? The nitrate only, okay? Then we'll address a few things that people messed up. So the 2 nitrates are gone, and that's what you're left with. Okay, some of you accidentally made it H2 as a gas. Hydrogen is a Brinkerhoff, that's true, but in this case, hydrogen was behaving not as a molecule, but as an acid. Okay, when hydrogen's in the front, it behaves as an acid. Okay? So hydrogen reacts with sulfur, and so what you would see is you'd have your acid slowly disappear, so the pH of the solution would slowly raise back to neutral, and then a gas, a horrible smelling death cloud of gas would start bubbling out of the liquid, and then you'd have some slurry that has got zinc left over and be a conductor. Okay? And that'd be the reaction. So the things I saw as mistakes is a few of you forgot this would be a gas, you made it a solid, and I heard that one question like, well wait, why don't we treat it as an alkali? Yeah, it is an alkali. It does behave as an alkali. However, this is a molecular substance that behaves as a gas. Okay, it's a weirdo. We'll talk more about why that happens when we get to bonding. Yes, sir?
Okay, so if you were to use, because NO3, okay, so if, say, like, one element has, I guess, 2 different charges.
Sure.
Would you use the charge for the whole equation?
Keep it whatever it was.
Okay.
If it starts as a 2 plus, keep it a 2 plus. If it starts as 3, keep it 3. In the end, there will be things that we call redox, where we will see their charge changes, but you'll have to see the whole thing to be able to do that. It's really difficult to predict those unless it's a single replacement or a combination or a decomp reaction. For double replacements that somehow become redox, you think I would say that. Double replacements are almost never redox, so when you see something like that, you'll have to see the whole equation as one. It's hard to predict that way. We'll get to those though later, so don't worry about that. So if it starts as a 2, leaves as a 2. If it starts as 3, leaves as a 3. If it's a 1, leaves as a 1. Okay? All right. Other questions on the question of the day? Anything else on the question of the day? Good, bad? Okay? Super nifty? All right, let me get this out of the way then. You guys want to go over some of the homework?
Yeah.
All right.
Oh, that's
Oh, that's okay. I'm hoping to get a little cheap wireless tablet that I can put up here and write on stuff directly instead of having this thing always in your guys' way. I'm waiting on installing the software for it, so hopefully that thing's days remembered of blocking your view. Alright, guys, Knowles, what number do you want to look at? 34A? Okay, 34A. Write the net ionic equation for the following molecular equation. HBr is a strong electrolyte. Okay, so it's telling you a hint that this thing fully associates. Alright, so we've got HBr plus NH3 goes to NH4Br. The H and the Br are going to fully break up. They're going to add to the NH3, which is a molecular substance. They're going to create NH4+, but the Br is still going to be hanging out on its own because now we have an ionic compound. Remember, ammonium is an ion. So what's the only thing that vanishes? What's the only thing that's common to both sides?
BR.
BR. Okay, that's it. That's it. Yes, ma'am.
Because it's all aqueous, isn't it?
Ooh, wait a minute. But this substance, yes, that thing is aqueous, but it's not decomposing. It's a molecule. Okay? There's no charged parts here. When hydrogen's in the back, it's not behaving like metal. If it were hydrogen in the front, then it's an aqueous. I think that maybe it's associated. There was hydrogen in the back. The other problem you have to run into is there are other substances that are also aqueous. This guy is aqueous. It's an acid, but it doesn't really dissociate very well. It's a weak acid. Same with good old acetic. Is also a weak acid. It barely dissociates. So aqueous doesn't always mean fully dissociates. It means dissolved in water. Okay? Be careful with that. Aqueous means dissolved in water. Dissociated is when they're broken into pieces. And that happens to strong electrolytes like ionic compounds that are fully soluble, strong acids. Okay? Not necessarily molecules. Be careful with that. What else on Z homework? She was asking if they're all aqueous. I think you were saying why isn't like NH, like N3 plus and H minus, something like that. Is that what you're saying? Yeah, and you won't do that because it's a molecule. It doesn't break down. Okay? Vanessa, I'm not sure what you're asking. I'm sorry. So, hydrogen and bromine break apart completely because it's a strong electrolyte. It's telling you that is the hint. Ammonium is an ion now. Bromide is an ion now. And we know that everything with ammonium, if you haven't taught those rules, they dissolve. Like bromine, iodine, chlorine, they will become a solid with things like with silver or mercury or lead, not ammonium. So this guy also brings up. And so you have the bromine on both sides being aqueous, unchanged, so you delete that. And you're left with an acid plus ammonium makes ammonia. What else on the homework? Anything else in the homework?
Oh, 36.
26. Potassium carbonate solution reacts with aqueous hydrobromic acid to give a solution of potassium bromide, carbon dioxide gas, water, right? The molecular equation. Okay, so we have potassium carbonate. We're adding that to some aqueous hydrobromic acid. Hydrobromic. It tells us it's going to make potassium bromide, which is aqueous, and then water and carbon dioxide, gas and liquid. Okay? Alright. The things that are aqueous. The potassium and the carbonate are aqueous. It's an ionic compound. So we started off with, bless you, 2 of these bad Jacksons. We had we're getting 2 hydrogens and 2 bromides. And it's going to make 2 potassiums, which are broken up, 2 bromines, which are broken up, and a water and a carbon dioxide. Okay? What things are the same on both sides? The potassium and the bromide. And so, what this says is you add acid to carbonate, you get water and carbon dioxide. That's the non-ion. Anytime you add acid to carbonate ion, you get water and carbon dioxide. Okay? I'm going to shut that door. It's loud out there.
Is it balanced though?
Guys, I'm trying to torture people here with chemistry. Alright, what else? 38? 38B? 38Z. Okay. Write the molecular equation and the net equation for the following. If no reaction occurs, write no reaction. So I've got barium nitrate and I got potassium sulfate. So barium and potassium are going to switch. And so you're going to get barium sulfate and you're going to get potassium nitrate. I'm going to get 2 potassium nitrates because each K plus needs 1 nitrate, which is a 1 minus. So the 2 Ks run off with the 2 nitrates and make 2 loving couples. Okay, barium sulfate, what do you know about it? It is a solid, right? But all nitrates are aqueous. So if we look, the nitrate and the potassium are going to stay aqueous. So essentially this becomes barium plus sulfate, turns into barium sulfate. Okay? Feel okay?
What happened to potassium?
Potassium, because it was aqueous in the beginning and aqueous at the end, didn't do anything, so it just vanishes. If it stays in the water and its form doesn't change, it doesn't change to a solid, doesn't do anything like that, doesn't change its charge, doesn't rearrange, it's a spectator. And you cross out the spectator.
So why'd you move barium over to sulfate?
Well, because it's a double replacement, and so the barium. So the reason why barium sulfate is a solid Barium is a 2+, sulfate's a 2-, and they have a very strong attraction to each other. Much stronger of an attraction to each other than they do to the water. They're two really foxy elements or compounds or whatever you want to put them respectively. And so they're going to stay together and come out of solution. Potassium, the nitrating, is being kind of fugly. And they're just kind of hanging out because they have nothing else better. But the water is also more interesting, so they'll also dissociate in the water on both sides. And so you have this really attractive couple that gets together and becomes the solid.
Okay.
The most attractive things are going to get together. Yes, sir? Well, they start coming in. Anything else? Feeling okay or not? Does that one make sense to you?
Yes.
Yeah. Do you want to see any other ones? Okay, then give me your homework. Pass it aside, please. That's okay.
The baby paper, I forgot a notebook.
So-
Not a baby paper.